Hello everyone. In today's video, I'm going to pick up from where we left off yesterday and finish up the reaction sheet. I fully expect everyone to have watched these videos and had some attempt at, understanding and memorizing the reactions so that we can move forward tomorrow um, and hopefully start learning mechanism and synthesis and nomenclature because the exam is coming up really fast. So yesterday, I stopped right here at the Corey House reaction. This reaction, just to remind you, is not required to understand, just to memorize and just kind of see how it works. Now, we've been doing a lot of reduction oxidation. It's a common trend here. And so in these reactions right here, hydride reduction of carbonyls. So we're using hydride, aka hydrogens that are nucleophilic per se, and we're going to use them to reduce carbonyls. Carbonyls are the carbon double bond O structures. So I'm going to put these up right here. Okay. And I know I'm not including the rules, but that's something for you to look at, but I will talk about it. Okay, so let's look at these reagents right here. So what we have carbonyl structures, right? We have electrophilic regions, and we have some sort of reagent, right? We have two of them. We have NaBH4 and we have ETOH, which is just ethanol, or they use ethanol in this case. And then the other one, we have LiAlH4 and ether and H2O plus. Okay, and let's look at what these do. So let's say let me make a nice clean molecule. All right, so now I've made quite a few sample molecules, and these are all just different carbonyl structures that you'll be able to you'll start seeing a bit more throughout Orgo 1, and a lot of these we'll see a lot more in Orgo 2. So there's certain rules when it comes to how we can reduce these carbonyls, right, or attack them. So when I'm using NaBH4 ETOH, what you need to know is that it's not a very strong nucleophile. Okay, it does not, it cannot attack the more complicated structures that I have on the bottom over here. So NaBH4 can only attack this guy and this guy. Okay, so only. Right, and what you need to know about LiAlH4, they do the same thing, but this one can attack all these. Okay, every single one, any variation of the carbonyl. So this one does everything. All right, and so I'm gonna get rid of these arrows. And the way this works, you need to kind of see this. So let's get rid of the spectator ion, right? No Na, right? We're going to have the bromine. Let's say we have these hydrogens, okay? And what we have here, we have the bromine is negative, okay? And that's why we have the Na. All right, so now that you know that, what we're going to have essentially, one of these hydrogens is going to come off and dissociate from the bromine, and it's going to act nucleophilically. So this hydrogen with its electrons is going to come and attack the carbonyl site and going to kick this up. And what I'm going to get in my product is I'll have this structure, I'll have electrons now, I'll have a negative charge up here, and then I'll have the hydrogen that we just added. Okay, so I'm reducing. Reduction is the process of essentially adding hydrogens to things, right, and increasing the electrons that carbon owns. Okay, so oxidation is the opposite, where I increase the amount of oxygen bonding. Okay, so I am reducing these oxidized centers, and so I'm adding a hydrogen, and then all that will happen is the ETOH will act as a proton donor, right? And so this is going to come, take this. All right, and then I'll get my my alcohol. So essentially, we need to understand that we're going from carbonyls to alcohols. Okay? All right? And so now I need to understand, and it's the same thing for this one. So this, remember this is called the ketone, right? And this is the aldehyde. Can't write. This is the aldehyde. All right? So remember that aldehydes are more reactive than the ketones, okay? But they may not be more reactive than the things down here, all right? So aldehydes are more reactive than ketones, okay? So this same process of attacking, right here, and this will kick this up. This carbonyl, these electrons in this double bond right here will always get kicked up to the oxygen because the oxygen is pulling those electrons, so that's where it's going to resonate. And then we just add hydrogens every time. Now the only difference between the NaBH4 and LiAlH4 is that the LiAlH4 is much stronger. So AlH4 can be used for other things besides aldehydes and ketones, whereas NaBH4 can only be used for aldehydes and ketones. So it's the same thing, right? And so this is going to come with one of its hydrogens, and it's going to attack. Let's say I attack this structure over here. Now this structure, it's not important for you to know what it is, but it's called an ester, okay? So this structure is going to get attacked, and this is going to get kicked up. Now this is going to be a demonstration of how all these mechanisms work over here. This is going to get attacked, and then it's going to get kicked up, and then we're going to get this molecule. So I get the minus on the oxygen, I get this and that, and now I have the hydrogen that I added. Now you might say, okay, it's time to protonate, go to step 2. But what happens is the electrons on the carbonyl come back down, and they come back down because I have a potential and possible leaving group on this molecule. So this is going to get kicked off, and the electrons are going to go onto this oxygen. And when that happens, I get this structure. I get a carbonyl, I get an aldehyde essentially, plus an O minus attached to this area right here. So 1, 2, 1, 2. So now I have this leaving group has left essentially, and then I'm going to do this reaction again. So I'm going to have another one of these hydrogens from the Al come and attack again and push this up. And what I'm going to get is I'm going to get the O minus, I'm going to get a hydrogen attached, I'm going to get a hydrogen attached. So now I have 1, 2 hydrogens that are attached. So what you need to know is that whenever I have a leading group, I have this reaction happens twice. Okay, and that's only because I have a leaving group that allows the carbonyl to reform. So I reform my electrophilic site. My electrophilic site gets attacked again. Okay, so this minus charge, right? Now we go to step 2. I introduce my acid, and this becomes an alcohol. So that's how we get the alcohol, and this also becomes an alcohol, right? So this is also present, and this also gets protonated. So I have these two things that form. Okay. That's just an example, and that you should be able to figure this out for the rest of the other examples I have over here. So if I erase this, okay, right. So let me keep that. Now let's look at if I do any one of these, right? So this is going to come and attack right here, push this up, right, and then this is going to come back down. Let me use a different color. Why not? And this is going to come back down in the next step and kick this off, right? And then for this one, it's going to get attacked right here. And by the way, you need to remember this. This also is the same process for the Grignard, right? We're reducing technically, but we're not adding hydrogens. We're actually adding carbon groups. So it's the same thing for these structures. If anything has a leaving group, that means we're going to have a double step, right? So it's going to happen twice. It's going to come back down, right? Chlorine is a good leaving group, and it's going to leave. And this would also come back down, right? This is a resonance stabilized leaving group, and it's going to leave. So nothing too complicated that's going on over here. So I hope everyone understands that. So just know that it's kind of a nucleophilic hydrogen that's coming and attacking these carbonyl sites, and that NABH4 can only do, they'll have it on the side over here, right? So they say reduce only aldehydes and ketones, use alcohols as a solvent. That's what they do. And then over here, reduce aldehydes, ketones, esters, acid halides, carboxylic acids, all on every carbonyl possible. Okay, so this is a very strong reducing reagent, and that's what we need to know for this. Okay. Now, not too bad, and most people, they don't understand the mechanism, so they don't understand, what's happening really. But if you understand it, it makes a lot of sense. Okay, and these can do the aldehydes and ketones as well. These can just do more things. So don't confuse that, oh, NABH4 is only for aldehydes and ketones. Right, but you need to remember that it's that it can only do those. But that LiAH4 can also do aldehydes and ketones as well, but it just does everything else. Now let's look at some other things. So we have now something called rainy nickel. So before we had all those H2PD or PT or nickel reaction, but here now we're going to have something H2RANI, rainy nickel. And the only difference between rainy nickel and the others is that the others could not reduce the carbonyl, right? As far as I know. The others could not reduce the carbonyl, but now using rainy nickel, it will reduce the carbonyl and will turn it back into an alcohol. So essentially, anything and everything that has excess electron density that's not fully saturated becomes fully saturated. So I get 2 hydrogens over here, 2 hydrogens over here, and this gets a hydrogen, and this gets a hydrogen. Okay, so everything gets fully saturated, and that's all we're doing. Now, this is one of my favorite things because people usually, you don't have to understand how this happens, but there's a little trick that helps, like to kind of make it easier to understand. Okay, so let's look at this. All right, and let's see. All right. So we have these reactions here, okay? And it seems like it's a lot, but it's only essentially 3 reactions that you need to know. They're just repeated for different alcohol environments. Okay, so you have secondary and they have primary, okay? And the same reagents. But they do different things depending on the degree of the alcohol, right? So what we're doing in this case, we're doing an oxidation. Oxidation of what? Alcohols, okay? So we're turning an alcohol group, right, some ROH group, and we're turning it into an R carbonyl group, okay? So that's what we're doing here, turning the OH into a carbonyl, all right? So the way I want everyone to think about this is, I want everyone to think of this as kind of like this. So let's say I have my alcohol, right? And I have a secondary alcohol right here, right? I have 2 R groups. And all this secondary designation, it has nothing to do with steric effects. It has nothing to do with that. What it has to do with is the implication. So the implication, when I say I have a secondary alcohol, that means I have an alcohol group attached to 2 carbons. Well, that means that I have a hydrogen here. So that means I have 1 hydrogen as my 4th group on this carbon where the alcohol is attached. Okay? And when I say primary alcohols, right, the implication is what? That this carbon right here has 2 electrons to another carbon, 2 electrons to an oxygen, 2 electrons to another hydrogen, and 2 electrons over here. So that means the implication is that I have 2 hydrogens. And this is the difference. This is the important thing. The amount of hydrogens that are present. And I can only ever have up to 2 hydrogens. I need at least 1 hydrogen for all these reactions. I need a hydrogen to oxidize. Okay? So let's look at the first one. Okay, so for secondaries, right? And then I'll look at primaries in a second. So what you guys need to know, for secondaries, for every single one of these reactions, okay, so I have Na2, CrO7, H2SO4, H2O. I have CrO3, H2SO4, H2O, acetone 0 degrees, called Jones. You can write this out in synthesis or in reactions. You can use the name Jones, okay? But what you need to identify is that this chromate. So chromate reagents are very oxidative, and that's another one of things that you need to be familiar with. So before we saw KMnO4 potassium permanganate is a oxidative reagent. So this is another very strong oxidative reagent, chromates, right? So these two I want you guys to identify as very strong, okay? Very strong oxidizers, all right? And I want you to look at PCC and I want you to think not so strong, right? And so what PCC is a anhydrous, right? It's anhydrous. And that means it's done without the presence of water. So these are done in the presence of water. It's aqueous, right? And so being in an aqueous environment allows, to my understanding, allows it to be more oxidative, okay? And so PCC is just, it's not as strong. So that's all you need to know, right? So it's not as strong, okay? And this will make sense when I show you the primaries, right? So for all of them, right, when it comes to secondary alcohols, all of them will essentially, we're going to think about it as I'm going to consume this hydrogen and I'm going to use its electrons to form the carbonyl, right? So I'm going to consume the hydrogen in every case and I'm going to use those electrons to form the carbonyl. And all of them, if I used any one of these, would give me this right here, okay? So all of them would give me this, okay? But when it comes to primary, I have two hydrogens, right? So now, for every single one of these reactions, I need to use, the requirement is to have at least one hydrogen, right? But if I have two, then it gets a little bit more different, right? So for my CR reagents, so Jones and the first one, right? Whenever I use those, they're going to consume one hydrogen, right? And they're going to form the carbonyl. Awesome, right? But what about the other hydrogen? Like we've shown before, whenever I have strong oxidizers and I have a free hydrogen, this is going to oxidize that hydrogen bond and it's going to turn into an alcohol. So what I get for the first two is always a carboxylic acid. So what they have shown over here is that if I have a primary alcohol and I use any one of these reagents, either the Na2CrO7 or Jones, I will always form an alcohol at a primary carbon. But PCC, on the other hand, will always give me the aldehyde, okay? So this one will give me this. And I will have this free hydrogen just chilling around, okay? So this one does not get used up. It's not oxidative enough to fully oxidize all these bonds that can be oxidized. So that's what you need to remember. And if you remember that, the difference between strong oxidizers and weak oxidizers, then you'll do perfectly on these reactions, and nothing will be complicated or confusing. All you have to do is memorize these reagents. So Na2CrO7, H2SO4, H2O, not that hard to memorize. And then this one's just CrO3, H2SO4, H2O, and then acetone 0 degrees. It's not that much of a change. So it's very, very reasonable to know this and understand it to some degree, okay? All right, so let's move on. We're almost done. Now I'm going to put these two, this reaction. I'm not going to show this one actually. So let's look at this formation of tosylate. So tosylate ester, and I want everyone to kind of know what this looks like. I'll put it up in a second. We have an alcohol, right? And here it's a primary alcohol. I don't think it always has to be a primary alcohol. It does not. And preferentially primary and secondary, because that's what we do SN2 on. But I have a primary alcohol or a secondary alcohol, and I use something called TSCl, right? And when I react it with TSCl, I'm essentially going to remove this hydrogen and I'm going to attach this TS group. And what that's going to give me, my OTOS. So OTOS is a very good leaving group that we used in SN2 and E2 and so on and so forth. And this is essentially how to form it. So if you need to form a good leaving group in the reactions, this is what we would use. So I'm just going to show what does TSCl look like? Okay. Let's see. I think it looks something like this. Okay, tosyl chloride. So essentially, it's something that has lots of resonance. It has a crap ton of resonance. I have this sulfur, which is even better at taking negative charges, but it won't be taking a negative charge. We'll have these oxygens here. So essentially, what we're going to have is, I'm going to have, right? So this is going to become an oxygen, right? When it's attached to the molecule. So I'm going to have that. This is going to be an oxygen, and I have like whatever the molecules over here, and this will leave, and this will be a very good leaving group. Okay, and so this will have a negative charge, and then I'll just have resonance. So resonance between these two oxygens and resonance with the ring and all this fun stuff. So that's why OTOS is such a good leaving group, because it's so much resonance stabilization that's going on. Now I want to look at these two reactions. Okay, I'm going to refresh the page. All right. Okay. All right, now let's look at these two. Very important to understand the distinction. So what these two reactions are doing are, we're going to go from alcohols to alcohol halides, right? So we're going to go to we're gonna be adding leaving groups to these molecules in replace of this alcohol. So X is always used to stand for halides, and so here X is going to be either bromine or chlorine. Okay, and what we do, so this is all you need to know. This is for tertiary, right? And this is a mistake I made, and I forgot. I didn't realize this designation was there. So this is only for tertiary, and this is for primary or secondary. So you have to use this reaction whenever I have a tertiary alcohol. I have to use this reaction. If I have a primary or secondary alcohol, I have to use these. Okay. So if I want to add a Br, I have to use this one. If I want to add a chlorine, I have to use this one. And if I want to add an I use this one. But usually what you end up always using is this. Just be familiar with these other ones. Okay, I just like using PBr3. And so essentially all that happens is, if I use HX and ether and 0 degrees Celsius, right, on a tertiary alcohol, it'll replace it with, so HBr, ether, 0 degrees, will replace this with a Br. Okay, so I have a Br here. Now for primary and secondary, it's the same thing. I just use PBr3, CH2Cl2, and it's for any SN2, SN1, whatever purposes that you're doing. And this will come in handy a lot in the synthesis. So these are two you need to be very familiar with, and just mainly these conditions, okay? So primary, secondary, and this is tertiary only. So that's just something you need to know. Oops, refresh the wrong one. Okay. All right. So now we're on the last page. Very, very nice. And so let's look at this one. All right. So I'm going to bring this over here, and I'm going to pause for a second and make some molecules. Okay, so now on the screen, you have a molecule with the alcohols on it and syn, right? So it has to be vicinal, diols must be syn, and I have Bruce Lee over here. Okay, so what I like to think of this reaction, my TA taught me actually. So this is HiO4, and HiO4, one way to remember this is it kind of sounds like hiya. So like when someone's doing like a karate chop or a kick, they make that hiya sound. So that's how he taught us to remember it. And if you want to think about it, Bruce Lee is going to come in and he's going to break this bond. Okay, so I'm going to hiya this bond right here, and this is going to break this. Okay. Okay, so Bruce Lee's gonna hiya that bond, and essentially we're going to get this. It looks a bit ugly, but essentially what happened was this bond in between the two vicinal diols, right? Diols. So all is the suffix for alcohols, and di just means two, and they're vicinal and they're syn, so syn vicinal diols. So they have to both be on the same wedge or dash. It doesn't have to necessarily be one or the other, but I have vicinal syn diols, and then this bond is going to be cut, and they're going to be oxidized. Okay, but it doesn't fully oxidize everything. So in the beginning, I have an OH and H over here, right? Mine is a little bit different. I have it just on opposite sides, but I have the OH and the H, and I have the CH3 and H, and this is just essentially just going to turn these into carbonyls, and I'm just going to have whatever group is there just sticking out. So either this or this, right? And it's just going to be a carbonyl. And that's all you need to remember. And you can remember it in the dumb way, just knowing Bruce Lee is going to come and attack. Okay? With a hi-ya. So that one's not too bad. It's easy to remember. And from here, it's pretty simple. So so formation of alkoxide anion. So if you have alcohols, right, primary, secondary, you can use solid Na to kind of fully deprotonate all of these. So just kind of like without introducing a base, you can solid Na will deprotonate all these alcohols and make them into O minuses. So Na solid, or for secondary and tertiary, you use K solid. And then we have the Williamson ether synthesis. So if you have RBr, and this is actually nothing actually complicated here. We have a strong base, right? It's not a strong non-bulky base, and we have a primary alkyl halide. And so this is just the SN2 of SN2 exception for E2. So we just have this primary alkyl halide, we have a strong base, and it's going to attach. And that's just one way of adding an OR group, forming an ether. Okay, so nothing complicated about that either. Okay, so this is easy. It's something you already know. Okay, now ethers from intermolecular dehydration. So we have two alcohols, and they can be any different. They can be different. Okay, so I can have any different alcohols, and if I use H2SO4 and high heat, 140 degrees Celsius specifically, you will form an ether. An ether is just an R group, an O in between them, and then another R group. Okay, so this is just one way to do it. And what they're saying over here must be identical. It does not have to be identical. What they're saying is if you want to get a good yield of a certain molecule, you need to use like identical structures. So if I use two different groups. So if I use, let's say, I'm gonna be general here, okay? If I use something called R, and I have ROH, and I combine it with R prime, and let's say it had a different number of carbons on it or structures, and I use H2SO4, 140 degrees Celsius, I would get combinations of ethers. So I would get the ROR ether. I would get the R prime O R prime ether, and I would get the R O R prime ether. So you get three different products versus if I used just one of these by itself, I would get just only this one. And that's what they're saying, okay? So just be aware that you can get a mix depending on what groups are present while you're doing this reaction, okay? So not too bad. I don't think you really need to know this one. This is more of an Orgo 2 thing, and even in Orgo 2, it doesn't really come up that much. But essentially, it has a very cool reaction. It's a very cool one. I would show it to you, but it's probably going to go over your head, and it's not that important. So just know that one of the carbon groups is going to shift over to the other one, and so whichever one is more substituted, you're going to have a methyl shift towards the least substituted one. Right, and so one of these will become a carbonyl, and the other one will gain an extra carbon, and that's really all there is for this. It says no mechanism, but you really don't need to. And then finally, one of the most important reactions out of all of these is the Fischer esterification, right? So Fischer esterification is essentially when I combine an alcohol So any alcohol plus any carboxylic acid. So I have an R group over here, right? So I have whatever, and I have an R group over here. And when I do this under the conditions of just H plus, right? H plus is the only thing I need to initiate this. I will essentially, what we need to think is this oxygen, this group over here is going to be gone, and what I'm going to have is this R, right? Whatever. I'm going to have the O, and I'm going to have this. Okay, so I'm going to indicate from where I have these things, and she might test you on this actually. So this oxygen is this one right here. Okay, and what you need to think about is this essentially is attacking. So because it's attacked, it's going to stay in the product and it's going to be there. This is the one that leaves because essentially it's a leaving group. So you need to think of this as the leaving group. And this is the nucleophile over here in this case. And then this is the electrophile, so this is going to be there. It's going to still be here. And so this and this are from these molecules. So the O from here is going to be from the alcohol, and the carbonyl and the R group are going to be from the carboxylic acid. Okay? And what the takeaway is that essentially I can have other things, right? So I can have this, and I can have an acid chloride too, because the concept is just essentially I have a leaving group here. So as long as something can leave, I can do this reaction, right? So as long as something can leave, I can do this reaction very nicely. So this is just a very important reaction, and what it gives us, this functional group is called the ester. This is the ester. I have an R, right? I have the O, I have the carbonyl, I have another R group. So essentially this structure is the ester, okay? So this is what we form. Fischer esterification. It's formed from an alcohol and some sort of either carboxylic acid right, or acid halide, okay? All right, and that's essentially it. That's the last reaction for this test and for the final. So some of these actually might not be on the final because she may not get this far, but it's only going to be either like the last few things that she doesn't get to, or something like that. But it's not that big of a leap. So essentially, by the end of test 3, you should be basically ready to take the final, except for one small final thing. So I expect everyone to be studying these and to be ready for whatever I have on Monday and Wednesday as well. All right, best of luck and study hard.